Okay, so this morning I promised that I would give you an idea of the proof for the local laws. So if you remember, the point is that we assume that we have the laws that we want on a cube of radius 2r, and we try to prove that then we have the laws that we want on a cube of radius r. Okay, so this is the sort of assumption. So we assume that we have that at level 2r, and with a certain constant c. Okay? And let me look now at the same quantity, but with qr. And I'm going to rewrite this f as the integral form. And you remember I abuse notation by ignoring the renormalization, and etc. So I write it like that. And now let's just write out the definition of this, right? So this is the log of a ratio of two things. So in the denominator, we put the partition function, because this is the expectation. So I can write k beta of mu. And let me add in RD for reference, so it means it's the original thing on the whole space, right? It's not a restricted partition function, it's the full partition function. And in the numerator, I'm just going to put the integral of e beta over 2 minus beta integral over the whole space. Okay, and then there's the d mu tensor n times. So this thing we're going to rewrite, because you see here I have the interior of QR, I have beta over 2, and here I have minus beta. And then in the exterior I have minus beta. So I can rewrite this as log integral e minus beta over 2 integral over qr minus beta integral in the complement. I'm going to divide by the same thing. Okay. So the first claim is that for the denominator, we can use the superadditivity of the Neumann partition function. So remember when we glue things with Neumann, so here is going to be QR and QR complements that are going to be my two sets. I can certainly write the thing with the u's, right? The grad u squared for the whole space. I can bound it by the integral over QR. So these ones are the ones solving with Neumann boundary condition. So this is just recalling something we said this morning. And in particular, I can write that. So this is the same really as grad h squared. I can write that k beta of mu in RD, which is this integral is going to be larger, so I'm going to bound this thing from above, so this thing is going to be bounded from below, than the sum of these two things. And there's a beta. Okay, so here what I want to do is I want to separate variables with the separation corresponding to the variables for the points that fall in the cube and the variables for the points that fall outside the cube. In all of these problems, the things are neutral. The configurations are screened. So I have to have a number of points in that cube, which is exactly this number. So I have to assume, in fact, before I do all this, I have to assume that this cube is a sort of quantized cube. It cannot be really an arbitrary cube. It has to be a cube in which mu integrates to an integer. Okay, so we assume that. Up to modifying a little bit the cube, we assume this is an integer. We call n bar this ideal number of points that should fall in that cube. Okay, so here basically what you're saying is you're looking at the probability, you're integrating over many configurations, and you're saying that this partition function is certainly at least equal to the situation where the configurations have exactly n bar points inside and big N minus n bar points outside. It's a sort of sub-event, right? It's a more restricted category of events, but if we want to bound from below, this is sufficient. And when we separate variables between the inside and the outside, we have a combinatorial term, which is going to be a binomial coefficient. This corresponds to the number of ways I can pick n bar variables out of big N, okay? Because we can relabel things. And so if we decide that the variables that correspond to the points falling in that box are the first ones in the category, I have to multiply by this factor. Okay, and then after that, I can separate variables, and I can just do this over QR and restrict to QR, if you want. And how many do I have? Now I have n bar, and the same outside. So it's the U for this QR. Okay, so now I'm restricted to the complement. And I have big N minus n bar points. So eventually I find this binomial coefficient, and now this is exactly my k beta of QR, k beta of QR complement. Okay, so this is by definition the product of these two things, because these are Neumann partition functions, and they make sense only if the number of points is exactly matching the integral in the set. Okay, so basically this is the sub-additivity of log k. The super-additivity of log k that I've rewritten in more details. So we're going to have this in the numerator. And for the denominator, so you see I have two parts, the inside and the outside. And I want to separate variables as well. So for the numerator, I want to bound from above. So there's going to be the same story. There's going to be a combinatorial factor that corresponds to how many ways I can pick the labelings of points such that I have little n points that fall in the cube. But now I have to consider all the possible values of that n. Okay, so n equals number of points that really are in QR. And now that's a random variable. Okay, so I have to sum over all the possibilities. And what I'm going to do, since I want to bound from above, it suffices to bound from below these energies. And these energies, by the sort of restriction property, it's always bigger than the guy with the V, because the V one is the one with the Dirichlet boundary condition, is the one that has the smallest energy. So I can bound e to the minus beta over 2, the one with the V. And same thing, but now for the outside, I have beta over 2, and here I have beta. Very important. Okay? So now we make the ratio of these two things. Okay, so we have to look at the log of the ratio of the sum. And in the denominator, I have n and. So here, what are we going to find? Well, this thing, by definition, is the L, what I call the L partition function. The one that corresponds to this should be a V. This should be a V. Right? So these are the Dirichlet partition functions. And this one has a beta over 2 and a little n. This one has a n minus n and a beta. And we're at the complement. Okay, so we're basically, for everything, separating between inside and outside. And the denominator, I have k beta of the complement. So this is what we're trying to estimate. So we have a bound from above by this. Okay, but now we know that we have good local laws up to size 2r. And in particular, this tells us that the number of particles that fall in that box does not deviate very much from n bar. Because if it was deviating a lot from n bar, you would have a lot of imbalance in that box. And in particular, it would also be imbalance in the double box. And so the f would have to be very large in the double box. And this we can rule out from the local laws. Okay, so there is a form of concentration at the higher scale that tells us that little n minus n bar is less than, okay, is in any case much less than RD, except with small probability. I'm going to remain vague on this, but you can make it more precise. Okay, so the concentration in particular tells us that. So n concentrates near n bar, and eventually what that means is I can neglect the sum in here. I can just replace it by the same combinatorial factor, and so I can formally cancel out numerator and denominator. And then we find ourselves with a very simple sum of logs. And we're almost done. If you have any questions while we mop, let me know. Yeah.
So it simplifies the binomial coefficients because n is close to the n bar?
Yes, except with small probability.
Okay, and so it's not that...
So in fact, I can reduce to an interval around n bar. Yeah. And there's going to be a number of points in that interval, but in the log, I can split it with, because I take the log, there's going to be the log of this error, this width of the interval, okay. And that's going to be much less than RD. It's going to be a log R, so I don't care about it. Okay. So it's not that there is just one term in the sum, but if you count how many terms you have, you see how big they are. Logarithmically, they are very... It's the biggest one that counts. Yeah. Well, standard, in fact, it's standard stuff, right? So you're bound by the number of things in the sum that count, and the log of that is very small. Because all you care about is that the whole thing is less than RD. Okay, so we started with this quantity, right? Log, expectation, e to the beta over 2 f cube r. We rewrote this as a ratio by definition of the expectation. And we find that it's bounded by this. So now I'm going to put some twiddles, but roughly, you see it's like the log of L beta of QR complement minus log k beta of QR complement plus the difference for the inside, but I'm going to just bound by the sum. So this one has this, and here I can put log okay? And so now the claim is that the first term, basically we've proven that things like that are small by screening. So the difference between the log k and the log L, that was precisely what screening does. So here we have to do a variant of what I described because we have a cube, and we want to consider, so this is kind of blocked off, and we're outside of this cube. And we want to take the configurations that are outside, and we want to screen them so that the Neumann boundary condition here becomes 0. So in fact, we're going to screen from the outside. So we're going to find a good contour here. We're going to erase the configuration here and replace it by points. So it's the same construction, just it's sort of reversed with respect to what the boundary is. So this one we call outer screening. The other one's called inner screening. But it's the same. Estimates are the same. And in particular, what matters is that even though this domain could be very, very large, the error that you're going to make is proportional to the surface of that small cube. So the cube is small, and it's the surface of that. That counts. OK, so the first term up here, we can bound. We can even bound in RD minus 1. OK, so there's something like that. By screening. And the, maybe there's a chi of beta, etc. And then these two guys, we just bound with a priori bounds. So this one is actually very similar to the one with k, again by screening if we want. And for the log k's, we have a priori bounds, which I didn't detail, but it's exactly the same as the a priori bounds when we have the whole space. You can check directly that these are bounded by C, beta, chi of beta, or D by a priori bounds. So you see here, it's not the same beta. There is a beta over 2, and there is a beta. So we're not trying to say that these are close. We're just bounding each of them separately. OK, so the screening was made possible here by the fact that we have the estimate at the slightly larger scale, and that gives us an a priori bound for the energy for most configurations, which is what I needed for this screenability property. So screening is only possible if you have some rough bound already. And now you can check that if you put all of these together, you can make this less than what you wanted. With this R. Okay, so that's completes the local law. So basically what screening does for you is that it allows you to do a sort of surgery where you can decouple the inside from the outside. And so you can compare the energy to the energy of things that are screened here and screened outside. And thanks to that, you deduce these local laws. So that completes that thing. And the other thing that comes together with this, this analysis is now we can get free energy expansions when we have varying background. Right, so we have a mu, and we already know that log k of 1 and qr divided by rd converges as r goes to infinity to some quantity that I called fd of beta. And there's a beta here, of course. So that's for uniform background. And we saw this by sub-superadditivity. But in the same way, we have sub-superadditivity for any mu, for any background. So what you want to do is, given a mu, you want to split your domain, or RD, into subcubes. Okay, so you want to split. So now, maybe from there we say, okay, now we want to do for an arbitrary constant, which is not 1, but which is m. So what is going to be the limit of that? So if you have a density m, a background charge m, it's the same as having background charge 1 up to a scaling factor, right? You want to change x into x times m to the 1 over d, and you can find a formula. So it's actually easy to compute. So I'll give you the answer. So it's something like that. And then there is an m log m. Okay, so minus, what did I do? Okay, so this is the limit when you divide by beta, I think. I think in the notes, so there's different conventions, but I think I decided to make it the limit of that divided by beta. And so then this one becomes m log m. Of course, the log case has this additive m log m, and there is a 1/4 in front. So it's written somewhere, but you have to find the right page, of course. Chapter 8. I think it's something like that. Let me put a beta over 2d. Okay, so here, remember, we're in the Coulomb case. So S is always d minus 2. So S is d minus 2. And this is what you get just by simple scaling. In particular, when S is 0, notice that when S is 0, here it's just f of beta. But if you're in dimension 3, for instance, or in dimension 1, so when S is not 0 in the Coulomb case, then you get a sort of effective temperature. You see the beta gets changed into beta times this. So there is a sort of effective temperature that depends on the density of points. Okay, and so now if you want to go to a general mu, what you're going to do is you're going to chop your space into small cubes of radius r, Of course, you want r to be much bigger than 1 and much less than n to the 1 over d. This would be the biggest scale. This is the smallest scale. In such a way that in each cube, mu is almost constant. Right? So we're going to assume that mu has some continuity property. And remember, this is a blown up of a nice density, typically. So when you blow it up, it varies very slowly. And so by almost additivity, the log k of mu q, or mu, sorry, rd, is going to be approximately equal to the sum of log k of mu I qi, and that is the average of mu in qi. All right, so these cubes have radius r. And what is the error that you make? It's a surface error. So for each cube, you make an error. So it's going to be, let's say, n n over r. So if you make r very small, you make a small error for mu minus mu average in each cube. Mu is going to be very close to its average if the cube is small. But you pay a lot of surface, because if you cut a lot, you pay a lot of surface errors. And this is why you see the 1 over r. And so there is an error which is also like in r, let's say, times n minus 1 minus 1 over d. So that's the error that you make when you replace mu by its average, roughly. Okay, so then the point is you need to optimize, right? You want to take r that's small enough that you make small errors when you replace mu by its average, but large enough that you don't pay too much surface errors. So this optimization leads to finding that, well, there seems to be a sort of optimal one, which is near n 1 over 2d. So it's like something in between, right? You don't want to be all the way here or all the way here. You want to be exactly in the middle. And so at the end of the day, we get an expansion with an error rate. So once we have replaced mu by a constant, we can use this formula. This is the formula for constant density. And then we can plug in and add. And so I'm just going to give you the formula, because we'll use it later. Okay. Okay, so final formula is this. Log k beta of mu in the whole space is equal to minus beta over 4 and integral of mu log mu. So that's the sum of these m log m's that got deleted. That's in the case s equals 0 plus beta n integral of mu 1 plus s over d f beta of mu, sorry, fd of mu s over d beta. And this gets integrated with respect to x, so it's mu of x. Plus an error which I will leave ambiguous, but it's strictly less than, it's a power of n strictly less than 1. Okay, so there is some positive gamma such that you have a rate, it's a bit like less than n. So you see all the terms of order n. So here this is order n, this is order n. Yes. So corollary is that we have obtained now an expansion of the original log z up to an error, which like that is n1 minus gamma. So something much smaller than n. And that comes from putting together the splitting formula with this formula. So if you remember, the beginning of the expansion was something like theta n e theta of mu theta. And there's a minus sign. And then there was some n log n term in the case of log interaction, and then plus this. Right? So minus beta over 4n, this with mu equals mu theta. Okay, plus this O. So again, I insist that we've made it so that all these errors, all these O's, are independent of n and beta. So you can play, again, you can play with beta depending on n. The formulas are correct. And so from a point of view of an expansion, you see how this, by the way, theta, it's also like beta and 2 minus s over d here. It's the same as that. So this is the leading order term. For example, n squared when s equals 0. And these are all lower order terms. And now we have access to the constant that is in front of n. And you can do the same at the level of energy minimizers. Energy minimizers would be, take this formula, divide by beta, and formally let beta tend to infinity. You see there's always a beta in front anyway. You can divide everything by beta, let beta tend to infinity, and you find a formula for the minimizers of the energy. So we've achieved this expansion to next order. And we're going to see that the coefficients that are at the order n, so for now they are interpreted with this function f of beta. But f of beta, we don't know much about it. It's some function. Tomorrow, I'm going to give you a variational interpretation for this function f of beta. That's going to relate to the microscopic structure of the configuration. So if you want the underlying point processes are going to be basically the things that are hidden at this next order. Okay, so leading order basically tells you the macroscopic behavior. Mu should look like mu theta. So the empirical measure should look like mu theta. And like the next order, it's going to tell you something about what the configuration should look like once you zoom and you look at the details of it. Another thing that's noteworthy, and we're going to use just a bit later today, is that you see the case s equals 0 in dimension 2 is particularly interesting because in the case s equals 0, for s equals 0, you just get beta over 4 n integral of mu log mu. And this term, you get 1 plus 0, so it's just integral of mu f of beta. So it's beta n fd of beta. But the mu integrates to a constant, right? So so it's just this. Yeah, I was a bit. Yes, I was a bit ambiguous on something. So I did this. I did this at the blown up scale, so I should remove the ends because everything gets integrated over this big box. So the correct statement is this. There's no n. And you see when you integrate mu, you get n. But when you do it back at this level of z, then it's correct. There is an n. So now this guy is not blown up. It's the original guy. And this guy is the mu prime, if you want. OK. OK, but if s equals 0, it's this.
What's the order of the error?
The error remains like this. Yeah. So this is correct. The error is like the volume. So you see, these terms are integrated in a thing that's of volume n. So they are, each of them is of order n. That's why I didn't need to put the n in front. I myself get confused when the scaling changes. So you see, when you're in this log case, interestingly, you have a term that's explicit in mu. It's actually the form of the entropy, mu log mu. It's not that it's the entropy here, it's that it's the log interaction. This term is not an entropy term, it's a logarithmic interaction term, happens to have the same form as an entropy. And this term is independent of mu. And that's very convenient, and this only happens in this logarithmic case. So what this allows you to do is, if you have two different measures, two different mu's, and you end up subtracting, for some reason, the free energies, which we will do soon, when you subtract, these terms cancel. And that's convenient because this term you actually don't know what it is. You don't know the value. So these things that you don't know cancel, and what you're left with are things that are very explicit. So that's going to be useful. Any questions? Yeah.
So what is gamma?
So it's some positive power that I didn't want to describe, but it's something like 1 over 2d.
Okay, it's between 0 and 1.
Ah, yes, between 0 and 1, of course. You cannot do much better than. So it's a small number. Think of something like that, 1 over 2d. What's useful is that it exists and it's positive. OK, so that finishes a chapter. And now I want to turn to another question that I mentioned at the beginning, which is the question of fluctuations of linear statistics. Okay, so this is going to be another way of measuring somehow the rigidity of the Coulomb gas. We've seen that the Coulomb gas is somehow quite rigid in the sense that if you, again, if you look at a box here and you ask how many points are in that box, the number of points is going to be very close to the integral of mu in that box. And the difference between the two is actually much smaller than what you would have for a Poisson point process. So there is much less fluctuation, or much less variance in the number of points than a Poisson point process. In that sense, the Coulomb gas is called hyperuniform. So hyperuniformity is something that precisely measures the variance of the number of points in a box and asks whether it's less than that for a Poisson point process. Okay, so the number of points in a box is much less than r to the d or 2d, I never know. Yeah, r to the 2d. Okay, so this you can you can get something like that just from the local laws already. The local laws are going to tell us a bound. So if we give ourselves give ourselves some test function. And I told you now, things are going to depend on the regularity of the test function. Taking an indicator function of a box, that's very different from taking a smooth test function. Here I'm going to give myself a smooth one. So sufficiently many derivatives. And you want to ask what are the linear statistics doing. So things like that, quantities like that, these are called linear statistics. And because we want to look at fluctuations, that means we might as well subtract off the difference between what you would find for the equilibrium measure, for instance, or for the thermal equilibrium measure. Maybe we do it like that. Okay? So we expect that this is going to look like that. But now we would like to know what's the size of the difference. So note, again, that this is the same as doing that. And this I can, if I want, because I'm in the Coulomb case, I can view this as the Laplacian of the potential. Hn that was defined precisely as convolution of G with this. Right? So if I want to control that, I could just control it by something like this. After integration by parts. And then I could do Cauchy-Schwarz and control by the L2 norm times basically square root of f. Right? Roughly, that's what I described a little bit. So the local laws that we obtain, so now it's really f QR, by the way. If Xi is supported in some QR, I could even have it with the restriction of f to that box. And so if the box gets smaller, I get a better estimate. And I would have some first bounds on it from the local laws. Okay, so the exponential moments of these types of quantities are controlled. But the claim is that what the local laws give you is good, but it's not sharp for smooth functions, for smooth test functions. We can obtain better estimates. Okay, so there exist estimates that directly come as corollary of the local laws and that basically follow this route that I just said with Cauchy-Schwarz. But there are better estimates than that. And that's what we're going to be after now. So actually, yeah, we could try to describe what's the size of this, but you see that this thing is going to be still very large, right? So if I'm in a macroscopic size thing, then macro seems to give me something like root n, right? Because this is like the volume. So this difference, we know that it's going to be bounded by root n, which is already not bad because this is a term of order n, this is a term of order n, and the difference is like square root n, so this is already saying something. Again, it's saying that there's a certain rigidity of the thing, you don't fluctuate, number of points doesn't fluctuate too much, etc. So what is the better estimate that we can get? So there exists a better estimate if Xi is regular enough. Okay, so that's what we're going to look for now. And the way to study this quantity, so this is a random variable, right? We give ourselves a Xi, and this is a random variable in the points. We're going to study the Laplace transform of this random variable. Or if you want, a moment generating function. So we're going to look at the log of the expectation of e to the t let's say sum of xi of xi. That will be enough because this thing is a constant. I can always subtract it later. Right? That would be the Laplace transform. But now for convenience, I'm going to want to scale things a little bit differently here. So I'm going to put minus beta n 1 minus s over d t. Why not? Because, well, if I want to get the Laplace transform later, I will set tau equals minus beta n 1 minus s over dt. And I will have a Laplace transform as a function of tau, which is what I wanted. Okay, so there's a transformation that allows me to go back to the standard Laplace transform. And we're going to see in a minute why I choose the scaling like this. Because if we write down what this is exactly, so as usual, an expectation, I need to define what, I just write what this is. So I divide by the partition function. I'm going to do it with z, sorry. The partition function of my original gas. And in the numerator, I put e to the minus beta n 1 minus s over d t sum of xi of xi. And I have to put the energy, right? Minus beta hn of xn. So it's a big ratio like that, right? So just definition of the Gibbs measure. E to the minus beta h, put this in front, divide by z and beta. All right, so now we can remember what h was. H, it's a sum of pair interactions It's defined like this. Okay? So in the H, and sorry, and there's somewhat important nuance here, is I need to put n minus s over d because this is the scaling that we've been working with. Okay, so I invite you to stare at this quantity, and I'm claiming that this quantity is just the energy, but with this external potential V changed into V plus T psi. So this is just like another external potential. Okay, so I have the same as this, I have the pair interaction, just I can combine this with that. And so my claim is that this whole thing is equal to log z for potential V plus T psi divided by z for potential V. Okay, with obvious notation. So now I retain the memory of what's the potential. So it's the partition function of the Coulomb gas with potential V plus T psi divided by the Coulomb gas partition function for V. Okay. So by the way, this method was pioneered by Johansson, who was the first to apply it in the context of the 1D log gas and obtain this way the convergence of the Laplace transform to that of a Gaussian. So now we see this way how important it is to understand the free energy, right? If you're able to understand those log z's very precisely, you have a chance of understanding these fluctuations. And what you need is to understand how the log z depends on the potential. You would like some explicit formula, ideally. Okay, but 15 minutes ago, I wrote on the board an expansion for log z. Right? It had a dependence in mu. It has these unknown functions f of beta. So we could try to plug that in here and see what comes out. The problem is those expansions had an error, if you remember, that's almost of size n. So if I plug in here log z of this plus log z of that, I'm going to pay these errors in any case. O of n 1 minus gamma, it doesn't seem like we're in better shape than the other estimates we got before. So this is not looking good for now. But we'll come back to it. So now the other remark is, in the end, we want to take tau equals minus beta, blah, 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 t, and we're going to take tau fixed, right? So we want to take tau to be of order 1. So that means that we need t to be tau over beta and s over d minus 1. But n s over d minus 1, that's always small. Because remember, s is d minus 2, so this is less than 1 in any case, so this is very small as n goes to infinity. So we're talking about having a small t. In other words, we're talking about making small perturbations to the external potential. Okay, so t is small. That's the only important thing here. Okay. So how does the partition function depend on the external potential? Well, we have learned in the beginning, thanks to the splitting and other things like that, that what the potential does really is it determines the equilibrium measure. And once you know the equilibrium measure, everything is determined from that, because you have the splitting that tells you that now then you can reduce to studying these new these reduced Gibbs measure for that mu. Okay. All right, so question, how does mu equilibrium depend on V? So now I'm going to call it mu V, because I want to remember how it depends on V. Actually, in the whole text, it's denoted mu V. Okay, but we've studied that a little bit at the beginning. That was the story about the obstacle problem, right? So if you remember, what we saw is that mu v is the indicator function of some set, which is part of the minimization problem. Laplacian of v over cd, I think. Okay, so there is some set that's the support of mu v, and we know its density here. What's this? Now, imagine I change v into v plus txc, which is what I'm doing here. Now, there's two cases. There's the first case, which is the nicest one. It's the case where the support of xi is in the bulk here. Right? So xi lives here, inside. So in that case, you're trying to measure the linear statistics in the bulk, right, where the points are. You could have another situation where the support of xi overlaps the boundary, or you could even, take xi here if you want, but you're not going to see many points here. So that case is harder than that case, because when you have xi here, you change v into v plus txc, the support of the equilibrium measure is actually going to move. Like it can make it move one way or another. So how it moves becomes a tricky question of potential analysis in PDE. We actually answered that question in the Coulomb case in a paper with Joachim Serra, and then in a paper with Thomas Leblay, we treated this question of fluctuations for test functions that can overlap the boundary. Okay, but for today, I want to stick to the simplest case, which is the case where it's inside. Okay, so assume the support of xi is included in sigma, which is the support of mu v. And then you can check, and it's not very hard to check, that in that case, the support doesn't change. So the sigma is going to remain the same. The only thing that's going to change is the v. It gets changed into, well, obviously v plus txi. So that is the new equilibrium measure. So this is particularly simple because we're in the Coulomb case. If we were not in the Coulomb case, we wouldn't have this simple representation. And if we're not in the Coulomb case, no matter what you do, the support is going to move, and you have to deal with that. And this is work in progress that we're doing with Luc Pelen to study the risk cases also like that. But, okay, so we're going to be Coulomb. And now I know how mu v varies. So this is mu v plus txi is mu v plus t Laplacian xi over cd. And remember, Laplacian xi is supported here. So I can really write this. It's actually exact. Okay, so now questions from there. We understand how mu varies when you change v into v plus txi. Essentially, physically, what this means is it's like you're applying a force to your system, right? You're applying an external force xi, and you're trying to see how the system is going to respond. And from this response, you deduce something about the fluctuations. So now I'm saying, okay, my equilibrium measure has moved a little bit. So I want to understand how the Coulomb gas changes, or its free energy changes. And the idea is, because it's a small perturbation, I'm going to try to understand how things behave by a transport. So I'm going to find an approximate transport which approximately transports mu v into mu v plus txi. Okay, so we have two probability measures. So there is a transport map from one to the other. Or if you prefer, it could be an optimal transport map. It doesn't necessarily have to be optimal. Raise your hand if the notion of transport map doesn't ring a bell. No? Yeah. Okay, so that means, in other words, that psi push forward mu v is mu v plus txi. Okay, I could try to find an exact transport map. There exists one. But it's more convenient to get a transport map that's approximate, but that has an exact formula. I want to have an explicit thing for psi. And what I mean by this is, in the limit when t goes to 0, this is this plus, if you want, plus little o of t, right? I want things that are the same plus little o of t. Or little o of 1 as t goes to 0. So that's actually easy to find. You can think of a continuity equation. So you can think either, okay, if you're familiar with transport theory, you say, okay, I need to solve Monge-Ampère, right? And then I'm going to say, okay, Monge-Ampère, it's a fully nonlinear equation, but we're linearizing, right? Because we're thinking of t goes to 0, so I can linearize Monge-Ampère. And you can look at what is the linearization of Monge-Ampère. Another way to think of it is, I want to find a psi such that div of psi mu, in the sense of my continuity equation the other day, is equal to minus dt mu at t equals 0. So this mu depends on t now. Right, that's the continuity equation. You're pushing in the direction psi, and that's actually the same as the linearization of Monge-Ampère. So in fact, what we need to solve is just div psi mu v equals, what is the derivative of this? Well, it's just Laplace and xi over cd. So you can check that if you solve this, you've, at first order, solved the transport problem. So this is the linearization of Monge-Ampère. And can we solve this? Well, claim is yes. It's easy. Take psi equals minus gradient xi divided by cd mu v. This is a map. Where is it supported? It's supported here, or in the support of xi. And where xi is supported, mu v does not vanish. So I can write the ratio. Right? I can divide by the density of mu v. This is well defined. And if you take the product psi times uv, you get the gradient of xi. If you take the divergence, you get exactly that. So it's an exact solution. So that's what's nice about this interior case, is that you have an exact solution. I mean, completely explicit and very simple in terms of xi. Okay, so now we have an approximate transport map. It's this psi. And we know exactly where it's supported, how regular it is, everything. So now the claim is we're going to be able to understand the change in the partition function by transport. So it's a sort of transport method that we introduced, which is essentially simply a change of variables. It consists in saying, okay, I have my initial gas. I'm going to push it in the direction of psi. I'm going to push everything, the points, all the charges. And I'm going to see how the energy changes when I push. So here's the mathematical formulation of that. So now I'm going to think, okay, I'm going to think at the level of k's. So what should I do? First, I should look at log z, of v plus t psi divided by z of v. And I should do the splitting first. So if you remember, this is going to give us some terms that look like n theta. It's going to be an n theta, e theta of mu theta v plus t xi. Minus e theta of mu theta v, okay, plus log k. So now here I'm cheating a lot. I want to cheat in the following way. I want to say that the equilibrium measure or the thermal equilibrium measure are the same. So in fact, they are not, but you see here the equilibrium measure is convenient because you can have all these explicit forms here. And the splitting, I described it for you with respect to the thermal equilibrium measure, but I told you can also do it with respect to the regular equilibrium measure. So I could just remove these thetas here and do this, and there's some other form that you can put here. And here you can do as if this was mu v. Okay, so for the purpose of presentation, I want to do as if they were the same. And what matters is here is you have something explicit, right? I mean, somewhat explicit. Certainly, it's deterministic, right? These are terms that don't depend on the points or anything. So these are things we can compute in principle. And when you expand them in terms of t, they're going to give you something like t squared times a certain variance, depending on xi, plus t times a certain constant that also depends on xi, plus lower order terms. Okay, so we save those terms aside. They will be useful later. But what we have to focus on is this term. So this is where I do my transport or my change of variables. And maybe let's not put the log for now. So it's a ratio of two integrals again. So it's e to the minus beta. And here I had fn xn mu v plus txc. And here I have mu v plus txc tensor n times. And in the denominator, the same. Yeah, I can just keep k. Okay? So this guy, mu v plus txc, we're going to use now that it's the push forward. This thing is the push forward of mu by t. And sorry, I made a mistake here. It's not psi that pushes forward. It's identity plus t psi. Okay, so when you want to solve, what you want to say is that there is a map that's very close to identity. And the psi that I solved for here is the perturbation of identity that it should be. So it's identity plus t psi pushes forward mu t into mu v plus t psi. So psi is fixed, but there is a t in front, and there is identity first. Okay, so everything is a perturbation of identity. And when you have a measure which is a push forward of another in an integral, well, you can just put the map inside the integrand, right? So you have the formula for change of variables. I'm going to erase here. Okay, so remember, if I have a function f, and I have a push forward of a measure, then this is just equal to integral of f of t of x d mu of x. Right? This is the definition of push forward. So I can do that in here. So this becomes equal to 1 over k. There's some n's. Everything has n's here. And now I'm going to get e to the minus beta n minus s over d. I'm going to put fn of phi t of xn, phi t push forward mu v. And what did I call phi t? I call phi t this thing. Identity plus tv, t psi. Okay, so this is phi t push forward mu v. It's a perturbation of identity. And now d mu v. Okay. And now I claim I can rewrite this as an expectation because I have 1 over the partition function. So it's the expectation of e minus beta n minus s over d. And I can put here fn phi t of xn phi t push forward mu v minus fn xn mu v. Because if I look at the expectation of that and I try to write out what it is, it's equal to exactly this ratio. Because this thing would be sort of canceling out with the Gibbs measure factor. So I'm looking at the exponential moments of something which is what? Which is the difference of energies between my system that has points at xn and density, background density mu v. So it's the positive charges and the negative charge minus mu v. And the system that has exactly the same charges but pushed forward by phi t. Okay, so I'm just pushing everything. And now I want to linearize this when t is small, because I'm thinking of t small. So I want to see, okay, what is this thing? It's going to be t times something. Right? You want a d dt, this thing. So it's identity plus t psi of the xi's. And to compute that, we have to remember what the definition of Fn was. So it was something like that, right? Okay, so you have to look at this expression. And you have to apply these sort of push forwards. So let's try to do the computation in our heads. When we push forward this, it just gives an identity plus t psi to each of these variables x. Yeah, so it's d dt x plus t psi y minus t psi. And then otherwise it becomes the same thing. So what happens when we differentiate with respect to t? If you evaluate at 0, for instance, or you just pick up a grad g dotted with psi of x minus psi of y, and then the stuff these charges here. Okay. So now this expression should ring a bell and remind you of something we saw yesterday. So you see it's something of the form v of x minus v of y dotted with the gradient g. So this is the variation of energy when you move things in a certain direction. We saw exactly that in the dynamics problem yesterday. When we differentiate the energy along the flow, well, the points get pushed by this velocity field, and the derivative of the energy has exactly a form like this. And it's not a coincidence. It's just, this is what happens when you take the charges, you push them by a transport, and you look at the variation of energy. It's equal to this. Okay, so this thing, I'm going to call it A1 of xn psi, xn mu in the direction psi. And what we proved yesterday, or what we actually saw, is there's this commutator estimate that says that A1, I can bound it by f, right? So Fn plus things like this. We could also go to second order. If you go to second order, you would get a Hessian here of g. And you would get psi of x minus psi of y tensored twice. And I would call that A2. So actually you can define AN. You can look at all derivatives if you want, but not very interesting. So call that A2. And in fact, there is also a commutator estimate for A2. There's also an estimate that says you can bound A2 by F. They're all bounded by F. It's really nice. Not obvious at all at the beginning. Though. And there is the n log n when you're in the case f d equals 2. Okay. So we have now this sharp result in a paper that's going to come out with Matt Rosenzweig. Okay, so if I put all of this together, we were here. And now I'm claiming that my thing that I'm trying to estimate, the log k and beta mu v plus txc, I can estimate it as the expectation E. So I'm going to differentiate this. I'm going to do a sort of Taylor expansion in t, right? So the difference value at t minus value at 0 is going to give me t a1. And if I want, I even have an error, which is of the size t squared times a2. That would be the next term in my Taylor expansion. I'm not going to be too precise on this here. So with that, I already can get something. Because we know that A1 is bounded by Fn. So we can already bound this. And let's neglect the quadratic terms because I can control them as well. So I have to take the log here. So I can replace by this. Now, what do I have here? I have beta n minus s over d, and I have a small t. But I have the local laws, or actually the global laws. I know how to control exponential moments of the energy. We control them by n. So when you have a small power here in the exponent, you can use Holder. So if you control, right? So if you have expectation, exponential e epsilon f, you can bound by expectation exponential f to the epsilon. Right, something like that. Is that correct? Yeah? Because I raise this to the power 1 over epsilon, and I do Holder. So when I take the log, I can bound this by absolute value of t times basically the expectation of f blah blah blah, which I know is bounded by beta chi beta n. Okay, by Holder. By Holder plus control of exponential moments. So by the way, if and there is the I forgot something here in the A1. There is the Lipschitz norm of psi. So this Lipschitz norm is floating here. So I should do this. And we can even say better, because if psi, okay, if xi was the test function, right? If xi lives on a very, very small region, then psi lives in the same region, because psi, I define it as the gradient of xi divided by nu. So psi is a transport that's supported in a very small region. And so I can even localize my estimates here. And instead of n, I could get rd, where r is the radius of the thing. So this can be made even better. But let's stick to the macro scale for presentation. So we have a test function, the macro scale, we get a bound like that. And now the claim is we've really improved things, because before we had a priori bounds that gave us estimates of this, each of them we know the order n, and we had an error n to the 1 minus gamma. But here, we have the t as a factor. So if t is very small, this is much, much better than the previous bound. So in particular, we get bounds like this by playing with the best t you can use while controlling the error terms. So there is some error terms here that correspond to these quadratic terms, and I didn't control them. And with this, you get a theorem, which I'll give you a sort of glimpse of. Which is something like this. So it's for all the Coulomb cases, right? So S equals d minus 2, but it can be in any dimension. You get that you control e to the beta n minus s over d, and here you put the sum of xi of xi minus n integral of xi d mu theta. So this is the fluctuation of your linear statistics. You control them by constants that depend on the norms of xi. Okay, so I'm not going to write down all the exact details of the constant, but they're in the notes. And if dimension is 1, it's a slightly different estimate, but there is an estimate too. So as I said, this is for 2 and higher. And you're going to ask, okay, we started from the Laplace transform of this. Where is that coming from? So that was coming from the explicit terms. I told you there are some explicit terms that come out, so we can just evaluate them. So in the explicit terms, there are some interesting terms there, and in particular, you get back this mean. So the consequence of this is it tells you, example, d equals 2, s equals 0, exponential moments of the fluctuations. So let's call this fluctuation of xi, this thing. Are basically bounded. So not something we knew before. Before I told you this thing is, we can bound it by square root n. But now it tells you, well, it's essentially bounded by 1. Constant depending on xi. If you want to go to dimension 3, then s equals 1. It's no longer the same statement. The statement now is expectation e to the beta n minus 1/3 times the fluctuation is bounded. So that means that basically your fluctuation is bounded by n to the 1/3. So you see, it's dimension dependent. It wasn't very clear what the order should be. Like even in the physics literature, there's some like conjectures, but it's not. Also, it's not clear that this is sharp. This is a bound, but is it the best bound? Not clear. Probably not, actually, in higher dimension. Dimension 2, we're going to see it's sharp. And so now, what we can do from there is we can actually go further in this case, the d equals 2, s equals 0. How are we going to go further? We're going to compare this expression, gives us an idea of the ratio of partition functions in terms of this term a1. And we had this other expression from before that I wrote on the board. I told you it's going to be very useful, that in dimension 2, this thing doesn't depend on the potential except via an explicit term. So we have, on the other hand, another expansion. I told you it wasn't good enough, but we're going to use it later. So the other expansion was giving us something that was like beta over 4n. So the n log n terms disappear. And I think there is a, so I don't remember actually the factor in front. I should probably look at it. There's 1 minus beta over 4. Yeah. Yeah, beta over 4 mu log mu. Okay, plus this O of n, 1 minus gamma, which is not a very good error, but that's what we have. So now this term, it's explicit and we can evaluate it. So you look at the derivative of mu log mu with respect to you write down exactly what mu v plus t psi is, and you compute, it's exactly going to be Laplace and xi log mu v. Okay, so that's an easy computation. And there's a t. Okay, so t plus little o of t, or o of t squared, in fact. Okay. So now we have two ways of evaluating this ratio. And we're going to compare the two ways. So this one was obtained with this super additivity, almost additivity, cut into boxes, get an estimate. We get this. And this one's obtained by transport. But they have to agree. Okay? So what are the errors that are made here? Here we have errors little o of tn, to be even pessimistic. And here you have errors o of n 1 minus gamma. So the trick is going to be, okay, let's apply this. I can apply this to any t that's not too large. Let's apply this to t, which is a small number, but independent of n. So some epsilon, but not something that goes to 0, just some epsilon. Then I'm going to make an error here, which is little o of n. And here I have an error o of n 1 minus gamma. So in that regime, this one is not so bad. It's not much worse than the other one. And because the two have to be equal, if you linearize here, when t is very small, epsilon, the leading order term is this. It's a1, blah, blah, blah. So because they have to agree, you find that a1 must be equal to, so remember, we're in the two-dimensional case here, so n is, s is 0, so I can just delete that. A1 must be equal to n over 4, or minus sign, log mu v. And this is true in exponential moments, in fact. So I can just take my two estimates together, compare them, insert this constant. This is a constant. I can insert it inside the expectation. I'm going to find that in exponential moments, these two things are not so different at leading order. Okay, so this thing that was the linearization of the energy, it's of size of the energy, so it's normal that it's of size n. And now we have an estimate for it. And so then what we can do is we can go back here, and then we can plug that value for the a1 that we have here. And this is only possible in this two-dimensional case, because in that two-dimensional case, this gamma here is pretty good. There's something hidden there. So plug in estimate for A1. And we get that the log of the ratio is now equal to, so the log of exponential thing, this, I'm going to estimate this by a constant, so it comes out of the expectation. And so it's going to be minus beta t, and there's a 1/4. And then I need to estimate this error term. And for that, I use that I have my second order commutator estimate. And this comes with a t squared. Plus O of t squared times the energy. T squared times the energy plus and 1 plus S over T, whatever. Okay, very nice. And now I have gained something because I have something exact. And I have my t squared in the errors here. So I compared the two evaluations by applying to t equals epsilon, and now I'm going to go back to t that's very small, because that's what I'm interested in. So what was the t that we cared about? If you remember, I wrote it on the board at some point. So for understanding the Laplace transform, we want t equals tau n minus 1 plus s over d divided by beta, and there's a minus. Okay, so now I'm in the two-dimensional case, so s equals 0, so it's tau over beta n. So it's like 1 over n. So think of beta as fixed here. So the log of the ratio, now I estimate it pretty well. So it's estimated by, so t is tau over beta n, so it's tau. There is a plus or minus here, I'm not sure. And what's in the error now? This is of size n, or n log n, and t squared is of size 1 over n. So it's going to be an error that's very small. And the other error is the one I pay from taking this and multiplying by t. So that was my error, my rate error, and I get to multiply it by t. So it's n to the minus gamma. So now, finally, we have an expansion with errors that are all very small. This is all little o of 1. Okay, so we started from something with an error little o of n. And because we have a t in front, and we're able to do a Hölder trick with comparing these two different expansions, we're able to sort of multiply the error by the t, and that gets us little o of 1 error. And so now I'm almost done. Because now we have an explicit expansion. And we can plug that back into the expansion for log z. We can plug that into the Laplace transform of the fluctuations. We have these explicit terms that I told you we could evaluate, and these give us terms like that. I have a term that's explicit, and I think there is a 1 over beta CD, maybe a 4, I'm not sure. So that's what comes out of the sort of constant terms. And from here and somewhere else, there was this mean that was coming out. There is this extra term. I think it has a beta. Yeah. Okay, so the formulas are not completely correct because I mixed up the equilibrium measure and the thermal equilibrium measure, but what matters is there is some expansion of this form, plus little o of 1 as n goes to infinity. And here tau is fixed. Fixed tau. Okay, so what have we obtained? We have obtained that we take the Laplace transform of a random variable and we write it in form m tau plus sigma over 2 t squared plus little o of 1. In other words, the log Laplace transform converges to something quadratic, and that's the signature of something that converges to a Gaussian. Because to show that you converge to a Gaussian, it suffices to show that the Laplace transform converges to the Laplace transform of a Gaussian, and this is your Gaussian, this is its mean, and this is its variance. Okay? So now we have a theorem. As a reward, as a compensation, tomorrow I'll finish early. Promise. Theorem. So this is Coulomb, D equals 2. Xi supported in the support of the equilibrium measure and sufficiently regular. I didn't discuss too much the regularity, but like say C6 or C7 or something. Then this guy converges as epsilon, as n goes to infinity, to a Gaussian of a certain mean. So there is a shift to the mean. Right, so this is the shift to the mean. It's not necessarily predictable. And variance 1 over CD beta grad xi squared. And if you look in your mental tables of Gaussian processes, when something has this variance, it's what's called a Gaussian free field. So in fact, what you can express from that is that H, which is the inverse Laplacian of this guy, of this, converges to a 2D, the 2D GFF. So this is a sort of complete and pretty satisfactory result in this particular dimension. It was proven by Leblay and myself, and there was a parallel result by Bauer, Schmidt, Bourgat, Nicolas, and Yao. And you can also prove the same theorem with Xi that's supported on small scales. So here Xi was a macroscopic thing, but you can make it supported on any scale as long as it's much bigger than the microscale. And the microscale in dimension 2 is n to the minus 1/2. A lot of things remain unsettled. For instance, what is the optimal regularity of Xi that you have to require? That's not settled. Can you do it in higher dimensions? Well, the only problem in higher dimensions is that the gamma, the rate that we have, is not good enough to finish the estimate. And you remember that we care about indicator function. So I want to mention that Thomas Leblay proved this theorem that was a sort of conjecture for a long time, which is this hyperuniformity. So the variance of the number of points is much smaller then r to the, I never know if it's r to the 2d. It should be 2d or d. D? D, thank you. So it's actually, he proved that it's less than rd to some log power that I forget. Okay, so you gain a little bit when r goes to infinity, and this is in blown up scale. Okay, so the variance of the number of points should be is much smaller than that of a Poisson point process, and that proves hyperuniformity, and it's again only 2D Coulomb. So that's pretty much the state of the art of where we are on that question. And tomorrow I will describe for you a large deviations result at the next order. So just like we expanded the energy, the free energy to next order, what lies at the next order, we can give it a variational formulation. We can give a full large deviations result in terms of the microscale point process. So this will be description. By the way, if you care about minimizing the energy, for instance, all the results here apply. You can just let beta be infinity. So instead of having a Gaussian, you will have a constant here. You see the variance goes to 0 when beta goes to infinity. And another remark is that there's also a theorem like that in dimension 1. So for the one-dimensional Coulomb gas, so be careful, one-dimensional Coulomb gas is not the log gas. Huh? So it's S equals -1. So when S equals 0 in dimension 1, this theorem was known for a while. There was works of Johansson, Boroguillonnet, Sherbina, so they proved a similar result in the 1D log case. But the 1D Coulomb case, which is not the 1D log case, it's proven for the first time in these notes. So I included it here. It's a new result. So it's higher dimension that's difficult. Any questions on this? Yeah.
So from the theory of optimal transport, we could know that the transport map per se could be expressed as some gradient of a convex function, and it is also cyclic monotone. Could this lead to some monotonicity of Laplacian of the energy?
You mean in the transport method?
Yeah.
But so in the transport method, because we are linearizing, we're looking at small deformations. Yes. Then all the maps are almost optimal, right? At leading order. So the one we have is the linearization of the optimal transport. So yes, you're asking whether you could use the fact that it's the gradient of a convex function.
So you calculate the A1 and A2, and J is also a Coulomb case, so there is also give the monotonicity of.
Right. The thing is, the map is this, right? The map is identity plus t psi. Yes. So it's the gradient, indeed, of basically of x squared over 2 plus t c. So there's something that looks a bit like that, but when t is small, yes, it's a convex function because the leading order is this guy, right? Okay. That makes it convex on its own. Okay. So I don't know what you can leverage from that. Like I don't. But near identity, everything's convex. Any other question? Yeah.
Yeah, for the expression, it seems we only need a test function to be C2, right?
Yeah, to make sense of the expression, it's true, but to make sense of the error terms, everything that's in the errors, that's where you see the derivatives of psi that come in. But yes, in principle, you would say, but even like H1 could suffice, right, just to make sense of the variance. Because this you can integrate by parts. You don't really need two derivatives. You could put the Laplacian onto the. And so that would be a nice conjecture that H1 is the borderline case, but we're very far from being able to prove that. Okay, well, thank you.